Hi everyone, my name is Radoslav and I'm going to be explaining one of the problems from the recent November challenge today. And here you can see some information about me. I have been doing competitive programming for quite a while, and today hopefully I'm going to be explaining pretty well the solution to one of the problems. So the problem we are going to be discussing today is Panic at the Disco, or like Panic, which was one of the harder problems in this round. There were like two hard problems. This was the first one, and then there was like another hard problem called Select Edge. And yeah, this one was more of a mathy problem because it required quite a lot of different theorems or like algorithms related to like linear algebra and linear recurrences. And yeah, like you can see that it requires some prior knowledge, but hopefully I'm going to explain everything pretty well. And yeah, I guess we can just go straight to the problem. So basically, I'm first going to explain the problem statement because it's actually relatively simple. And then I'm going to talk about the first two subtasks, but I won't really focus on them because that's one of the like complicated problems. So yeah, I'm mainly going to be talking about like the last subtask, which is the hard one. And actually it turned out that most people didn't solve the problem in the intended way, but they actually found an additional solution, which, also when I was solving the problem, I discovered this, in a way, easier solution, although it's not that much easier. But the intended solution is actually pretty fun, so I'm going to split the video in three parts in a way. Like, first I'm going to talk about the first and second subtask, then I'm going to focus on the easier solution, which is, it's easier to come up with. And finally, I'm going to discuss the intended solution, which is pretty fun. And in a way, like, there is a pretty nice trick, which you can actually use in some other problems. So yeah, I guess we can just go straight to the problem statement. And yeah, let's leave the slides now. And I'm going to start explaining it in the browser. So yeah, in a way, we're basically just given a k by k matrix, M. And after that, they just mentioned that MRC will be just the cell at row R and column C. And we are interested in calculating this S matrix. Like S is a matrix, which is given by the sum of n. But basically, like, S is in a way like the sum of FA plus ID, which in a way is like, F is basically the Fibonacci number, like the A plus E multiplied by D Fibonacci number multiplied by this matrix to the ith power. And in a way, like, this kind of resembles a geometric progression. However, we can see that the coefficients here aren't really the same because in a way, like, the Fibonacci numbers also grow. And yeah, basically we have this summation and we want to find the matrix. It's pretty trivial, the problem statement. We are just given A, which is AD, which are just two integers, then M, which is our matrix, and also we are given N, and we just want to find this sum. And in a way, like, it's just the sum of a certain Fibonacci number multiplied by the matrix to the ith power for every I from 0 to this N, which is also given. And of course, this, as you can kind of guess, this sum grows exponentially. Yeah, that's pretty obvious because, like, even in the power of the matrix, we have I, and like, obviously this grows exponentially, so we also want to calculate this modulo this number, which is just a prime number that's commonly used. Some people may think that the problem is related to FFT or something like that, but actually that's just a random prime number, I guess. Like, the intended solution doesn't really use the fact that this prime model actually has nice roots of unity. And okay, yeah, I'm pretty sure everyone is familiar with what Fibonacci numbers are. So yeah, I guess like the problem statement is pretty clear. And now I guess let's just quickly go to the constraints. So we have to solve t-tests, but that's pretty common. And the main constraints are k, where k is like the size of the matrix. and it's up to 100. And then the tricky thing is that actually the power of our sum is very large. It's 10 to the power of 1000. And yeah, I mean, I guess you can see that this can grow pretty fast. And yeah, I mean, basically, everyone probably will already see that you can do a kind of stupid solution, which is in complexity k to the cube. All right, maybe not everyone, but like the more experienced people could actually see that you can easily solve this recurrence in k cubed multiplied by log n. So it's just like the standard matrix exponential solution. However, that's not enough. And yeah, I mean, because like the logarithm of 10 to the 1000 is like 8000, and okay, not 8000, it's 3000, and you also have to multiply this by k cube, and yeah, that's pretty large. So yeah, for the first two subtasks, the solution is actually pretty cool, and I'm gonna start by explaining how we will solve it. So yeah, let's just switch to my notes. All right, so we have this M, which is our matrix, which is a k by k matrix, and we have like our n, and f of n is the nth Fibonacci number. And again, the problem statement is simply to compute this value, modulo our model. But I'm just gonna like avoid writing the modulo everywhere because it's just inconvenient, and you can just assume that everything is in the field modulo m. And yeah, let's just to simplify our, just to make our lives easier, let's denote the prefix sum till position k as s of sk. So yeah, basically sk is defined as basically this summation, but for the first k positions. And yeah, obviously then our answer is simply s of n. And yeah, like now going to subtask 1, the main idea is that in a way we are going to create a vector where each of the elements is actually a matrix. This may be kind of surprising, but the main idea is to have a vector where every element, the first element will represent but basically the pth position. Okay, so yeah, let's consider v of p, which is basically a vector where every element will be a matrix. And in a way, we want to calculate such a v so that our answer will be the last thing in the vector. So in a way, like v of p will have 3 elements. The last element will be s of p minus 2. So it's basically, we are interested in finding v of p plus 2. So that this thing, we are interested in finding v of n plus 2. So that the last thing here will be basically our sum. And like the first 2 elements of this vector, again, remember those are matrices, will be basically, when we consider the sp minus 2 sum, it will just be the last 2 elements of this sum. So in a way, like obviously we have some sum, and every term of the sum will be of this form. And in our vector, we'll just keep the last 2 terms from this sum. I mean, in a way, like our sum is sp minus 2, so yeah, we simply will basically like keep the last term in this sum, which is basically this thing. And then we will just keep like the one after that, which is in a way not included in this sum, but we can easily calculate it by using, I mean, it's just, we can just use the Fibonacci definition and easily find the next one. But the thing is that we can actually compute v of 0, as that's pretty trivial. And in v of 0, we'll basically just have the sum will be 0, then here we will just have m to the 0th power multiplied by one of the Fibonacci numbers, and the other one will be just the 0 matrix. And yeah, so the main idea is, in a way, we know that, like the main idea is that we kind of want to to easily get v of n, because like n is very large, and in a way we just want to compute this thing pretty fast. And like the trick we are using here is that every element of V will basically be some matrix. And in a way, you can say that the field here is just the matrices, the K by K matrices. So yeah, what we can see is actually that if we want to get VP, if we want to get VP plus 1 from VP, we can actually find a matrix of matrices. So basically, like every element here is a matrix, such that when you multiply this matrix by V of P, you'd get VP plus 1. So like what we want to do is to basically just solve the recurrence relation. I mean, normally when we solve some recurrence relations, we just do matrix exponential, when we just create some matrix. But now we want to find some matrix. We want to solve a recurrence relation where the elements are matrices instead of just integers. And surprisingly or not, I mean, like if you have studied some linear algebra, you know that you could also do this thing with the elements of the matrix being also matrices. And that's pretty much the trick. You can, like normally if you wanted to do this for integers, you would have something like the matrix I'm going to write now. It would be like some, so like in a way, when you want to get VP plus 1, you want to basically get the, so like the first element of VP plus 1 should be the, so the second element of V plus 1 should be the first one of VP. So in a way, like this Fibonacci number multiplied by MP minus 1 will just be this Fibonacci number multiplied by MP minus 2 for the next position. So in a way, like if we just write the 0 and 1 positions, because they're pretty easy, the whole thing should look something like that if you wanted to compute it for just integers, because like this way it will basically just do this. And now when we actually talk about matrices, the only difference is that instead of the zeros and the ones, we'll have either the identity matrix, which is the whole diagonal being 1, or we'll just have a 0 matrix there. And I mean, the whole trick is basically just doing the same recursive relation as when you do the integers, but instead of just having integers, having matrices at every position. And obviously you can do everything by the same way. And the only problem here is that we actually don't know the recurrence relation. We know that it's, we can in a way like define it by C1 and C2. So like in a way what we are expressing is VP plus 1 from VP as a recursive relation based on two coefficients C1 and C2. And like C1 and C2 should satisfy the fact that FA, I mean basically like the fact that the Fibonacci numbers of this kind of weird form, which is like basically this form is in a way arithmetic progression, because it's like a plus I multiplied by the difference of the arithmetic progression. And like, yeah, in a way, if we find C1 and C2 that satisfy the following equation for all Fibonacci numbers, then if we just create this matrix, obviously like if we find C1 and C2, then we can easily create this matrix, like matrix of matrices. And I mean, if we have this matrix of matrices, we can easily compute just the power of this matrix to the nth, and then just compute Vn plus 1. And this would just be the k cube, because like, I mean, actually it would be 27 multiplied by k cube, because here we have some, if we want to power this matrix of matrices, inside of it we'll have matrix summations and matrix multiplications, and those are normally done in k cube. So yeah, basically we'll have k cube from there, and apart from that it will be 27 because we have a 3 by 3 matrix and we want to matrix multiplied, so it's like 3 by 3 by 3, which is 27 by k is k cubed, and now by log n, which would be enough for the first two subtasks. However, we still have this small problem that we don't know how to find C1 and C2. And here comes one of the prerequisites for this problem, which is basically the Burley-Camp-Massey algorithm, which is basically imagine you have some sequence and you want, and you know that it follows some linear recurrence relation. And basically like the Burley-Camp-Massey just finds the smallest or like the shortest such recursive relation. And it works in, and I mean, if your sequence has length n, then it will work in n multiplied by basically n by minimum, where minimum is the smallest length of such a recursive relation. And for the Fibonacci numbers, you can literally just generate, as we know that the Fibonacci numbers will follow just two numbers like that. So it's just enough to generate like, I mean, the easiest thing to do is to just generate, for example, the first 10 things and just run Burley-Camp-Massey and you'll be fine. The thing is that you surely need to implement the algorithm because the A's and D's in this problem are different. And in a way, you can't really find some universal C1 and C2 because they'll most likely, and I mean, yeah, they will just depend by A and D. So yeah, basically the idea for the first two subtasks, at least one approach, because maybe there are some other approaches, is to create this matrix of matrices, which is based on those two coefficients. And then by powering this matrix of matrices, we can just get like the vector, which just represents two numbers, two terms, and then the sum. And yeah, that's pretty much it. But yeah, the full solution is much more interesting, so I'm probably just gonna go to it now. If you're interested, I'm probably gonna link here a tutorial for the algorithm because it's one of the, I mean, in some harder problems you definitely need it. So yeah, if you haven't implemented it before, or you haven't, if you just don't know the algorithm, I advise you to first read it and then continue to the editorial, like I mean the Burley-Camp-Massey. So yeah, the first subtask is basically the same as the previous one, but instead of k less than or equal than 20, we have k less than or equal to 100. So yeah, now we have like a larger constraint for k. And as I already mentioned, there are two solutions. One of them is quite easy, but by easy, I don't really mean that it's that simple, but it's easier to come up with. While the other one is the intended solution, and it has a pretty cool trick. So I'm gonna start with the easier solution. And yeah, basically what we are gonna do is try simplifying our equation, like the sum we want to find. Because in a way, let's look at the Fibonacci numbers. You don't really want to have something that complicated in the index. So in a way, if we can expand this Fibonacci number, then maybe we'll get something easier, which we will be able to work around. However, unfortunately, we're only given the recurrence relation for the Fibonacci numbers that's based on the previous term. So in a way, on the previous two terms. So in a way, even like the problem is that here, if we just use the normal definition of Fibonacci numbers, we'll just decrease this ugly term, like ugly index, by 1 and 2. And this won't really help us because we want to decrease the inner part with the I. But fortunately, if you're familiar with some, I mean, I'm pretty sure quite a lot of people have already heard that there exists this formula for Fibonacci number that's basically with the golden ratio. And yeah, basically it is known that f of n is equal to phi of n minus 1 minus phi to the n over square root of 5. where phi is basically 1 plus square root of 5 over 2. So the thing is that obviously phi is irrational because it contains square root of 5. And in a way, like if you use this definition, you'll be working with floating point numbers, which isn't the best thing because in general, we have some model and we want to use the model. And also, unfortunately, for some modulos, actually square root of 5 will exist. So like there'll be some number k such that k squared is equal to 5, like k squared modulo m. However, for our modulo, we don't really have a square root of 5. So that's kind of annoying. But we'll be able to fix this issue. For now, let's just ignore it and let's assume that we, in a way, can handle floating point numbers. And let's just say that we can easily divide by square root of 5 or just multiply by square root of 5. So yeah, let's go to the sum. We have that the sum of n is equal basically to the Fibonacci number of a plus I multiplied by d multiplied by this matrix, which is m to the power of I. And we can just like open the brackets, like we can just replace f of this weird term with the formula we had over there. And I have skipped the deriving here, but it's just like opening the brackets. Not even opening the brackets, we just split f of n into two parts. The first part being the one with the phi, and the second part is basically the one with 1 minus phi. And we'll get this following sum, which is symmetrical in a way between the two sides. On the left side, we have some constant, which is like phi to the power of a over square root of 5, multiplied by the sum from 0 to n of phi to the power of d, which is again a constant, multiplied by m, and the whole thing to the power of I. So the whole thing is to the power of I because you can see that in the Fibonacci number, like in the index, we had I multiplied by d. So in a way, like the phi was powered to a plus I multiplied by d. And in a way, we split this thing. The phi multiplied by power of a goes outside, while the phi to the power of d multiplied by I goes inside, and we just use I as a common power. So yeah, in a way, this thing inside is a constant because d is a constant and phi is a constant. And yeah, overall, right now, we just want to find the geometric progression of some matrix. And the new matrix is basically m prime, which is phi to the power of d multiplied by m. So anyway, like if we just get like this matrix, which is inside, we find its value, which is easy because we already know m. We can easily find phi to the power of d. Then we just need to find the geometric progression, like the sum of the geometric progression with basically just this matrix. And in a way, we just completely remove the Fibonacci number, which is pretty good because it simplifies our lives. However, here, again, we have the problem that square root of 5 doesn't exist in ZF modulo. So like, we don't really have the square root of 5. But here, this is a pretty cool trick. It's common in some of the problems. And I mean, if you haven't seen it before, I guess it's kind of hard to come up with it. And the idea is to actually, instead of considering just the field of the integers, let's consider a new field, which will be for some pairs, x, y, and they'll represent x plus y multiplied by square root of 5. In a way, like that's similar to complex numbers, but there you have like x plus y multiplied by e, where like I is square root of minus 1. And yeah, in a way, like we'll consider this new field, and now we'll define the, we'll just represent that xy will denote the x plus square root of 5 multiplied by y, modulo our model m. And the cool thing is that now let's see how the addition, subtraction, and multiplication will be defined. So basically, if we have x1 and y1 as the first integer, not the first integer, but like the first thing in our field, and x2 and y2 as the second, Then the addition is simply just like the component-wise addition. Yeah, it's basically just x1 plus x2 and y1 plus y2. That's obvious because, I mean, if you just sum the actual representations, then you'd have like square root of 5 multiplied by y1 plus y2, and same for the x1 and x2. So, I mean, we do the same thing for the subtraction, and now we need to see what happens when we multiply two things. And it's actually pretty simple. You just multiply. I mean, we again use the, I'm just gonna undo the previous thing so that you can see it in a nicer way. If we just look at the definitions, which are like x plus square root of y, you just need to multiply you just need to do the pairwise multiplication. So like the integer part will be just x1 multiplied by x2. Then then also, like when you multiply y1 by y2, you'd have two square root of 5s. So it's like square root of 5 multiplied by square root of 5 multiplied by y1 multiplied by y2. So it's like the fully integer part of the result of the multiplication would be x1 multiplied by x2 plus 5 multiplied by y1 multiplied by y2. And obviously for the part which has like the square root of 5 coefficient, it will be just y1 multiplied by x2 and x1 multiplied by y2, like their sum. So yeah, here are some examples how we'll represent some integers in our new base, in our new field. So if something is completely integer, then we just represent it as 5, 0, because like it doesn't really have a square root of 5 part. Then something which is similar to 2 square root of 5 will be represented as 0 and 2, because we don't really have a fully integer part, we just have the fully square root of 5 part. So yeah, it's 0, 2. And then something which is similar to 1 over square root of 5. So if you remember in the phi, we had this thing. We can actually rationalize this thing and we'll get square root of 5 over 5, which is actually 1 over 5 multiplied by square root of 5. And for this thing, we would use modular inverse. Yeah, I'm not going to write it here, but yeah, it's modular inverse. And yeah, I mean, in a way, like all numbers that have a square root of 5 part can be represented now as two pairs of integers, such that the integers are between 0 and the modulo minus 1. And yeah, that's pretty useful. So yeah, I mean, because we already defined the addition, subtraction, and multiplication, the division is basically the same as the multiplication, so I haven't really added it here. But yeah, I mean, when we have all of those, we can just easily compute. I mean, we can easily see that our field satisfies all properties, and instead of just doing everything on integers, we can just do it on this x plus y multiplied by square root of 5 field. And maybe something here that is tricky to see is that actually, because in the end, we know that the Fibonacci numbers are always integers, then the answer in the end will always have a 0y. So in a way, like somewhere in between, maybe the y will be positive, but in our final answer, only the x's will be non-negative. The y's will always be negative because we know that everything is integer. Because like this formula in the end should yield an integer if we don't use any doubles. So yeah, basically like we just, in a way, instead of doing all of the operations on integers, we'll just do the operations on the pairs, where the operations are defined in the way I mentioned below. So yeah, now we basically, going back to our problem, I already mentioned that now we just basically need to evaluate something of this form. So we have some matrix M prime, where M prime is basically some constant, which in our case was like, I mean, in a way, like we actually need to do the whole solution twice, first for the left part and then for the right part, but that's the same thing. We just multiply by a constant of 2, like our complexity, and we just do this separately. So yeah, in a way, like, as phi to the power of d was constant, we can now simply, I mean, our task is simply to calculate the sum of, basically like the sum of the geometric progression with this new matrix, which is m prime. And I mean, the standard way to do this is just matrix exponential. We create like, I mean, yeah, it's just like it's the standard problem, and you use matrix exponential to solve it. And the complexity is k cubed multiplied by log n. In a way, like, you actually can use this solution for the previous subtask if you find it easier. Because, like, I mean, if you discover this thing about the basis, then the k cube multiplied by log n solution is very simple. You simply just have a matrix and you want to find the sum of the geometric progression. And yeah, to actually optimize it, there is a theorem we always use. I mean, in general, like, it's a pretty useful theorem, which we used when we can't really do the k cube solution for matrix exponential. And it's like the Cayley-Hamilton theorem. And basically, like, what it says is that a matrix is always a solution to its characteristic polynomial. And I mean, if you just hear this, maybe you don't really know what I'm talking about. So I'm gonna try explaining this. So imagine that we have this matrix M. Like, now let's just completely forget our problem statement. Because, like, we already kind of simplified our problem to just finding the sum of the geometric progression for some certain matrix. And, like, that's why now let's just try seeing what this Cayley-Hamilton theorem does. So it says that every matrix is a solution to its characteristic polynomial. Or in other words, that the determinant of x, where x is some constant or maybe something else, multiplied by the identity matrix minus m is equal to 0. So yeah, like, it basically says that when we replace x by m, then the determinant will be 0. In a way, it's easy to see because, like, you just multiply m by the identity and subtract m. So obviously, like, inside you'll have just 0, and the determinant of 0 is 0. But I mean, this is just an intuition. It's obviously not. I mean, it's obviously not. How should I say it? It's not very formal because, in a way, now I'm gonna just extract the definition of the determinant of x for an integer x. But, like, the Cayley-Hamilton theorem says that if you just extract the determinant in terms of x, and then you replace x by m, then it will satisfy this equation. So in other words, let's just look at an example. Let's have m being this matrix. So yeah, it's just like, you can see it here. And now let's calculate x multiplied by the identity matrix. So x by the identity matrix will be just the matrix where we have x's on the diagonal. And let's subtract m from this matrix. So in the end, we'll have this thing. So yeah, I mean, everything will be negative, and basically we'll add x's to the diagonal. So yeah, if you actually work the details out of the determinant, I mean, yeah, you just do the standard thing. You multiply this, and then subtract the other ones. You'd get that the determinant of this thing is x cubed minus x squared minus 3x minus 8. And, like, basically the Cayley-Hamilton theorem tells you that if you get this determinant and you replace x by m, and I mean, like, obviously when you have a constant, you also multiply by the identity matrix because m is a matrix, while here for x we were just working with integers. So in other words, like, the Cayley-Hamilton theorem just tells you that it's just fine to replace everything with m, and it will be correct. If you're interested about the whole proof, feel free to check it out. I mean, you can literally just Google Cayley-Hamilton, you go to Wikipedia, and you'll see the proof of the theorem. But the interesting part is not why this works. You can just kind of assume this, because normally you use this thing in some complicated problems, I guess. And yeah, what you have is that, I mean, you have this equation, and now for our example, we can see that we can express m cube m cube by m2 and m squared and m and some constant. Or in other words, like m cube will be a polynomial of m of degree 2. So yeah. So yeah, I mean, like by directly applying the Cayley-Hamilton theorem, we get that we get a closed form for m3 for m cube. But what will happen when we try finding m to the 4th power? So let's work out the details. So it's like, if we have m to the 4th power, that's equal to m multiplied by m to the 3rd power. But the thing is that we actually know m to the 3rd power as polynomial of degree 2. Or in other words, like we know m to the m cube, and if we just apply the definition we already found, we would decrease our degree by 1. Because like we express m cube as a polynomial of degree 2. So basically like the degree decreases by 1. So yeah, let's just continue working out the details. So we'll have m multiplied by m cube. Yeah, as you can see, we basically just replace m cube. And now let's open up the brackets and we'll just get the following. However, now that again we get m cube, so we can simply just reduce the whole thing again. So this term will actually again go to that, and then we can just sum up the coefficients and we'll get this new polynomial. But the thing you can notice is that it's again of degree 2. And you can see that we can just continue this procedure. We can compute m5, and it will be again of degree 2, and so on and so on. So we can easily generalize this, that if we have used the Cayley-Hamilton theorem and we have found the representation for m cube in our example, then we can easily find the representation for everything above that. So like we can easily go from mk to mk plus 1 in O(n) squared time. It's n squared because in a way like we need to sum some coefficients. So yeah, now the cool thing is that, so okay, actually I'm gonna try showing what's the problem with this thing, because like, okay, we can actually find mk plus 1 from mk. However, we can't really find a representation for, I mean, the whole thing is quite slow, because you just increase the power by 1 and by 1 and by 1. So the trick here we want to use is in a way binary lifting, or like trying to get from mk to m2k. So in other words, like if we find how to do the transition from mk to m2k, we can easily find m for some large power of n in logarithmic time depending on n. So yeah, what we actually do is actually pretty simple. So imagine we know mk, then we can, so like mk is obviously a polynomial of degree 3 right now, for at least for our example. So yeah, like imagine that the degree is actually n for our polynomial. So we can actually compute mk squared with the naive polynomial multiplication in O(n) squared. However, now the degree of this new thing will be actually, so yeah, like we have something that's of degree 2 times the degree of mk. So it's the new degree will actually be 2n minus 2. But we actually, if we just consider the same thing as before, we can actually see that we can do the reduces. So in other words, like because the degree is quite large, so it's like, it's not quite large, but it's like twice as large as we want it to be. And we actually have some terms which are for before, I mean, some of the terms will be m to the power of n, m to the power of n plus 1, and so on until m to the power of 2n minus 2. But we can actually reduce this thing to a polynomial of degree n minus 1. Same for this one, and same for all of them. So in a way, like, we can reduce everything and it will just increase the coefficients in n squared time. So in a way, like, if we have mk as a polynomial of degree n minus 1, then we can easily get m to the power of 2k, again as a polynomial of degree k minus 1. As a polynomial of degree n minus 1. Yeah, pardon me about that. And all of these transitions are basically done in n squared time. So what this shows is that we can compute mn, which is in a way what we want, as a polynomial of m, because like, I mean, the whole idea of the Kyle-Hamilton theorem is that everything is expressed as a polynomial of m. So yeah, like, in a way we will just compute the coefficients before m to the 0th power, m to the 1st power, and so on until m to the n minus 1st power. And yeah, in a way, like, if we want to compute m to the nth, then we can do this in complexity ok squared multiplied by log n. So this is talking about like the original problem statement, where k was the size of the matrix. So because like we showed that the number of coefficients is the same as the size of the matrix in a way, like the number of rows or columns in the matrix. And yeah, in a way, like, if our transitions are with complexity O degree squared, and we need to do logarithmic number of jumps, then obviously the whole complexity will be k squared multiplied by log n, which you can see is actually better than the previous thing we discovered. The only problem here is that, okay, so we do have this complexity, but unfortunately, this only computes the coefficients before m to the 1st power, to the 2nd, and so on. So we need to somehow actually find a final answer. And yeah, before that, actually, we know that we have computed mn. Well, like, we know how to compute m to the power of n. However, that's not our problem statement, because we wanted to actually compute the geometric progression. So there are actually a couple of ways to go around this. One of them is to actually use the definition of geometric progression, and there is like a way to actually compress this thing, but it requires matrix inverses, and we aren't really sure whether m actually has a matrix inverse. However, there's another way to notice this, and it's to actually see that the degree of the polynomial, well, like the sum matrix, will actually be just one larger than the degree of mn. So in a way, like, we knew that mn has degree k minus 1. So then the sum of the m's will actually have degree k, which is pretty useful. It will just have degree 1 above the current one. And I mean, if we actually know that, we can easily get a full solution. So we'll start by just computing the characteristic polynomial. One way to do this is basically by just using the determinant and actually finding the inverses. But yeah, I mean, like, there are different ways to do it. One way is to do this, for example, you can just use Gauss or something like that. However, there is also another way to do it, which requires the Berkeley-Massey theorem again, algorithm again. We will just compute the first couple of s's, we'll run the algorithm, and then we'll actually have a recurrence relation. And if you have this recurrence relation, we can just easily find, I mean, a large power of it using the same approach. So yeah, I mean, like, in a way, we just want to find the characteristic polynomial. There are a couple of ways to do it. So yeah, I mean, you can literally just go to the solutions and see, because I mean, right now I won't be going into details how to do all of these things, because they're more or less kind of technical, and that's not the interesting part about the problem. So yeah, you can compute this characteristic polynomial pretty fast. So yeah, either in k squared or k cubed time, but I mean, it's good enough. It's not multiplied by log n. And now what we want to do is basically, here we do the Cayley-Hamilton theorem, and we actually do this lifting part, which will basically give us k squared log n as the time complexity to actually find the coefficients for the final sum. But now we also need to compute m squared, and so on until m to the power of k, because we do have the coefficients for the thing, but we also need to find the actual x's in a way. And yeah, like to do this, the easiest way is to just use k to the fourth. You basically just multiply it by 1 by 1. I mean, you just multiply the matrix by m. And yeah, I mean, like, finally, when we actually have the coefficients and also the powers of m to the, like, the degree of our polynomial, we simply just calculate our answer, which can be done in degree multiplied, because like the coefficients are integers, so we just multiply this integer by every element of the matrix, which is k squared, and then we just sum two matrices, which is again k squared. And as the degree is k, so we have like a OK cube complexity to actually just sum our answer when we have computed the m's and also the coefficients. And yeah, this gives us the overall complexity of k to the fourth power plus k squared multiplied by log n. And yeah, that was enough to pass it, because like the other solution has k cubed multiplied by log n, and log n is actually way larger than k in this case. So yeah, I mean, the solution was enough to pass, and that was the first idea, which is kind of simple. And I mean, the main trick, I guess, was the fact that you can actually express the Fibonacci numbers in this field, which is basically like x plus y multiplied by square root of 5. It's a pretty cool trick. I mean, normally you can, if it's just Fibonacci numbers, you can solve almost all problems with Fibonacci numbers using this way. In a way, it's cheaty, because I mean, like, normally that's not the intended solution, because as far as I know, not a lot of people know it. At least I think I have seen it just once in some comment section, and yeah, it was pretty cool seeing how to just easily get a solution if you know this trick. And yeah, I mean, like, maybe try thinking about this if you ever see again some harder problem about Fibonacci numbers. And yeah, that's the first trick. And maybe the second one is I mean, after that is just how to use some theorems. Like, maybe it's pretty cool how to actually, instead of just computing the whole answer, to just compute the coefficients and then multiply the coefficients by the matrices to the powers we need. And yeah, I mean, like, that's the first solution. If you have any questions, just leave them in the basically either the discussion in the editorial, or you can just leave them in the YouTube video, because I will be looking at the comments and I'm going to be answering them, because the problem is quite hard. So yeah, I feel like maybe not everything will be completely clear, but hopefully it will. And yeah, I mean, that was the first solution. And now I'm going to go to the one I actually found pretty cool. And yeah, actually, just to recap what we know so far, the intended solution, I mean, I guess I would say it's harder just because one of the parts, I mean, at least it was pretty new to me, and I didn't know that you can actually do something like that. So yeah, let's just recap what we know. So we already know that mi is a polynomial of degree k. Another thing we know is that f of this ugly term inside is a polynomial of degree 2. This can be easily shown by the, I mean, like you can easily construct a 2 by 2 matrix that will show that this thing is a polynomial of degree 2. And I mean, like, if we have these two things, then obviously the product of the two things, because they in a way depend by I, like both of them, is obviously a polynomial of degree less than or equal to 2k. Because I mean, you just multiply all of the terms by each other, and the degree can't really exceed 2k. So yeah, we can just say that it's a polynomial of degree 2k, and if the degree is smaller than that, we will just append it with some terms with coefficients 0. And I mean, like, trivially, by using the observations we had above, and we already did them, if we actually do the sum of this thing, I mean, we already have this thing, and now we sum it from 0 to n, this thing will actually be a polynomial of degree less than or equal to 2k plus 1. So in a way, like, if you just have any recurrence relation that is a polynomial, yeah, imagine you have just any recurrence relation, which is a polynomial of degree, for example, z, then the sum of this sequence from 0 to n will actually be a polynomial of degree z plus 1. And that's like always the case when we have linear recurrences, and it's a pretty useful trick which you actually apply in quite a lot of problems which relate to like characteristic polynomials or something like that. So yeah, I mean, like, the easiest thing to do is simply to compute. I mean, we just showed that our answer is a polynomial of degree less than or equal to 2k plus 1. So in a way, if we just find the coefficients of our polynomial, we can just use the above discussed solution with like the binary lifting and like reducing the polynomial again and again and again. And we would just get like the coefficients for s of n. And I mean, if we just have those coefficients, we just apply the previous solution, like the trivial parts of the previous solution. Like the part in the previous solution you need to find is basically the thing about the fields and how to actually express the square root of 5. And I mean, like, in this case, we won't really need this thing, because like we just showed that if we have this thing, then our answer will be simply a polynomial of degree twice as large as in the previous case. But that's just a constant of 2, so that's fine. And I mean, let's just compute the first 2 multiplied by the degree terms of our s. So in a way, like, we compute s0, s1, s2, and so on until s4k plus 2. And then we just use Berlekamp-Massey to actually find the coefficients. But unfortunately, we have a problem here, because don't forget that our answer is actually a matrix. So we can't really apply this thing because it's for integers, and we actually have matrices. So in a way, yeah, we can't really find the Berlekamp-Massey coefficients if we have matrices. And fortunately, we can actually use this probabilistic trick. We'll encode by 2 random imagine, let's just create 2 random vectors. And those vectors will be L and R. And L will be 1 by k, and R will be k by 1. And now let's compute. So we will basically compute L multiplied by S0 multiplied by R, then L multiplied by S1 by R, and so on, until like L multiplied by S4k plus 2 multiplied by R. And we can notice that all of those matrices are actually 1 by 1. So they're basically integers. And the final observation is that actually the coefficients we'll find with high probability will be the same as the ones for the matrices, because you multiply everywhere by the same 2 vectors. And then, like, if something satisfies, I mean, this basically means that with very high probability we'll actually find a valid solution. And I mean, another way to actually ensure this thing, you can actually do a couple of tries for L and R. So like, you generate it once, then you generate it a second time, and the third time, and a fourth time. And yeah, like and if just, so like the thing is that this way, if you just like compute this L multiplied by S multiplied by R array of numbers, and you run the Berlekamp-Massey, you'll get some coefficients. And you can actually easily check whether those coefficients are correct, because you can just try finding the matrices and see whether they match. Because like, you're sure that the coefficients will match for L multiplied by S by R, but you're not sure whether they'll match if you just have the matrices. And I mean, like, it's an easy check, but I mean, overall, what you can do is you just generate 2 vectors, you do the Burley-Camp-Massey, you find the coefficients, and then you see whether those coefficients are correct. If they're not, you just generate L and R again. But for this problem statement, I mean, the probability to actually fail this thing is very low, so even just generating the coefficients once was enough. And I mean, I think this is a very cool trick because it actually shows that we can easily find a recurrence relation even for matrices by just using the Burley-Camp-Massey. So in a way, you just don't have any other details. You simply find the first couple of terms of our recurrence relations, which was like S. Then you create two random vectors, which are L and R. You create this one by one small matrices, and then you just use Burley-Camp-Massey to find the recurrence relation. And when you have the recurrence relation, what you do is you simply use the algorithm discussed in the easy solution, which, I mean, basically the binary lifting to actually find the coefficients. And I mean, yeah, like we'll find the coefficients of the polynomial for Sn, and then you just need to multiply it again by m to the first power, m to the, not m, but like by S0, by S1, and so on. Because this time we'll actually have S as our term for the polynomial. And the overall complexity will again be k squared log n, although here the coefficient will be 4 because the polynomial is slightly larger. But this is actually the fast part of the solution. The slower part is actually to when we have the coefficients to actually build the final answer matrix, which again stays k to the 4th power. And I mean, that was pretty much the problem. I think it was longer than the normal editorials I do, but I hope you enjoyed it. Again, if you have just any questions, leave them in the chat because it was a harder problem. So if you have just any doubts, I'm going to be answering them. And yeah, I hope you enjoyed it. And yeah, it was, in my opinion, it was one of the cooler problems. So yeah, I guess let's do the outro, and thanks for watching. I guess subscribe to the CodeChef channel because there'll be some new things coming, and yeah, you can also join the Telegram channel. Thanks again for watching, and I guess see you next time.